I'm in Minitab with the hand group data set, and we're going to look at just testing this assumption of equal variances that I have mentioned a couple of times. Now, SPSS does the test automatically for you, but the output is so nasty that I don't know that it's very easy to read. So every time I come into Minitab, I just think it is so much nicer to look at. So to test for equal variances, and this is one of the assumptions that we have in our t-tests, and well, for the t-test there's two versions of the test, one with equal variances and one without, and then for the analysis of variance, one of the assumptions is that we have a similar amount of variation in each group. So just to show you what I mean, we're just going to go back to, actually I've probably got a box plot here already, window, box plot of hand grip strength. So the question is, do we have a similar amount of variation in each of these groups? And in this case, we probably do, just because of these outliers here, which is going to increase the variation. You can see that this group here is a little bit more compact, as in they're a little bit more tightly packed together. So without the outlier, that would give us a smaller amount of variation, but with it, that's going to increase. Now, to do a test to see if these variances are in fact the same, we go to Stat, ANOVA, and Test for Equal Variances. And I'll bring this over from the other screen. So I've already done this, but I'll take these out. I always have to do everything first just to check I can remember how to do it, because I don't do these tests a lot. So the response is average hand strength. If we were looking at hand time, then we could do that one instead. In this case, we've been looking at arthritis. Confidence level of 95 is fine. You can give it a title if you want. It depends whether or not you're going to need the plot. You can always change that afterwards. Okay. So this is what I love about Minitab. This output is just so easy to read. We've got a nice plot here showing us the estimate of the variance in each of the groups with the 95% confidence interval. Then over on the side, we've got two versions of the test for equal variances. Now we're just going to use Levines test, which is the bottom box here. Now the null hypothesis for variances is pretty much the same as what it is for everything else, and that is that the variances are equal, or that there is no difference in the variance between the groups. And we are hoping that we can accept this null hypothesis, because this is our assumption for the analysis of variance, is that they're all equal. So the null hypothesis is that all the variances are equal. Over here we've got a p-value of 0.241, which is very high, so we have no evidence against the null hypothesis, and therefore we will accept that the variances are in fact equal. And the reason I like this output is that because we've got these 95% confidence intervals, this is actually on the standard deviations, which is related to the variance, but it's close enough for our purposes. We can see that even though there is a difference in the amount of variation, they all overlap. And so the true value could well be the same. So if you're being picky about this is the Bonferroni confidence interval for the standard deviations. The standard deviation is the square root of the variance, so they're related to each other. And we've just been using Levines test here. Now the question is, what do you do if your variances are not equal? So if you have one variance which is really low and one variance which is really high. I wonder if we could find that. Should we just quickly try, see if we can find one where they're not equal? Now I have a feeling that the variances are equal for gender. Let me think. I don't know what residence means. Let's try it. No, they're equal as well. What else have we got in this data set? Arthritis condition. Again, I'd have to go back to the README file because I don't actually know what condition is coding for, but we can still do the test anyway. I wonder if that's the condition they were tested under. I seem to remember now actually that they were testing, here we go, this is interesting. So they were testing, I think, hand grip strength in the presence of a younger person to see if having a young person next to you changed how strong you were. But again, go back to the README file and have a look at what condition has been coded for. But what I'm interested in here is looking to see that actually here is a case where we've got a lot more variation in condition 2 than we have for condition 1. So to see how that works, we can go to graph and let's try a dot plot just for fun with groups. The graph variable hand strength over condition. Okay. So you can see here that the hand group strength for condition 1 is all grouped between 0 and 16, whereas for under condition 2 it goes from 0 all the way up to about 28, 30. So we've got a lot more variation under condition 2. So if we were doing a t-test for this, we would choose the option that says the variances are not equal. So where are we? Basic stats, 2 sample t. Take out gender and put in condition. And this here, assume equal variances, we would uncheck that. We're not going to assume equal variances. And it just does a slightly different version of the test. Now with ANOVA, you don't have a choice to do that. So if you had more than 2 groups and you were doing an analysis of variance, one of the assumptions is that the variances are equal. If you violate that assumption, that is if the assumption does not hold true, as it is in this case, the question is what do you do? Now in most cases, you would actually, depending on how severe the violation of the assumption is, and it's not too bad in this case, we had a look at those dot plots, you would probably continue on, but you would have to acknowledge the fact that your assumption is not met, and you would have to put a little statement in there saying that the test for equal variances showed that the variances are probably not equal in this case, and therefore the results should be interpreted with caution. The thing with ANOVA is that it's actually very robust, and what can happen is that even if the assumptions are not strictly met, it will keep running. So it's a bit like an old car that's broken down. Things keep falling off it, but the car keeps chugging along. And so ANOVA is a really good workhorse in that even if the assumptions are not quite met, it often still gives you the right results. So for the purposes of this subject, because we're not going into transformations and going more advanced into our data analysis, if you find out with your data that the assumption of equal variances is not met, that is you get a low p-value here and you have to reject that null hypothesis, continue on with what you're doing and just acknowledge the fact that there are some problems with your data and we need to interpret the results with caution.